All right, back from break, and as you could tell from lecture, the first part of this, the first part of chapter 23, there are some subtleties and some details to how these quantities are related. So if you are a little nervous or a little uncertain or a little worried about some of what we've gone through, I would say start looking at some of the homework examples or go back through some of the examples we've done here. The important feature for us is to be able to set up problems and solve them. So we're not going to be looking at, I don't think any of our homework problems are going to have any of these detailed integrations going on. These are mostly in terms of deriving formulas that we can then use. So the formulas that we have derived in these lectures, for the most part, the detailed ones, you can, or the ones where we've gone through and done the details with the integrations, the formulas that we've come up with for the general formulas for electric potential, for example, you can work from those. So let's get back to electric potential due to point charges, due to charges. And what we found is that looking at these spherical distributions, the electric potential is equal to K. Now that's little k. They've written this as 1 over 4 pi epsilon naught, but that combination right there is the same thing as little k. K times Q over R. If it's a negative point charge, it's still KQ over R, but Q is now negative. And so just by definition, we use plus and minus signs on our electric potential to let us know if we're closer to a bunch of positive charge or a bunch of negative charge. Now another formula we're going to want to have develop here is how much potential energy is stored in bringing two charges close to each other. Now they're calling this work. What minimum work could be needed to bring two charges close to each other? Now they're actually saying that one of the charges is just sitting there and the other charge is brought in closer and closer. But you know, when we think about this, what we're really doing is we are taking two charges, two positive charges, here they are, 3 microcoulombs and 20 microcoulombs, and we're taking them from a situation where they were separated by an infinite distance, and what we're doing is we're bringing them closer. Now these are positive charges, so if they're both positive, then it's going to require, it's a repulsive force, it's going to store up potential energy by bringing these closer and closer together. Now I put the gravitational example in here just for a comparison. Gravity is an attractive force, and that means that there's a minus sign here. That means that I don't have to put energy in to try and bring two objects close together gravitationally. Gravitationally, the potential energy goes negative. So in this example, where the force is attractive, I actually have to do work to pull them apart. So that minus sign is reminding us that we're kind of in an energy debt. If two objects are attracting each other, then when they're close together, we have a negative potential energy, and in order to separate them, I have to put energy in to bring them back up to 0. If the force is repulsive, then the potential energies that get stored up are positive. So for repulsive forces, the potential energies will be positive. For attractive forces, the potential energies will be negative, kind of following that same diagram we had here in terms of electric potentials. Okay, so let's go in and calculate the amount of energy. The amount of energy we're going to need to bring two charges closer to each other is given by this formula. So this is important for us, KQ1, Q2 over the distance of separation. Now what this formula says is if the distance of separation is infinitely large, the potential energy is 0. That's the same definition we use for attractive or repulsive forces. Whether attractive or repulsive, at a separation of infinity, the potential energies are defined to be 0. And then what happens is the objects come closer together In the attractive force case, potential energies will be going negative. In the repulsive force case, the potential energies will be going positive. And we can plug into that formula. So here is little k, Q1, Q2, distance, not squared. This is potential energy, it's not force. So it's not distance squared, it's just distance. And when we calculate this, I am ending up with 1.08 joules when they are separated at 50 centimeters. And then as I bring them even closer, I can see that the potential energy is going up. So, and I'm guessing, is that what they talked about? No, so I've changed that. So I added part of this in. Yeah, so at infinity, there was 0 potential energy, and then as I bring them closer, and then even closer, the potential energies are going up. And that's how much energy would be required to push those positive charges closer and closer to each other. Now, the energy is being stored, so when I let go, the charges will fly away from each other. I've stored up energy by bringing those positive charges close to each other. Okay, this was an example we did with electric fields. We had a couple of charges. This is 50 microcoulombs. That one's minus 50 microcoulombs. And so what will the electric potential be at point A and point B? Now, one of the really nice features of electric potential is it's a scalar. It's not a vector. So because it's not a vector, I don't have to work in terms of components. I don't have to think of how much potential in the X, Y, and Z direction. I can solve this problem. Let's take a look and see. What we can do is think of a picture kind of like this. Here is a charge, and the only important question is, how far am I away from that charge? So if I'm located here, I don't have to think of that in terms of components. I just have to think of what's the value of little r. Now, if we go back to the picture just before, what that's saying is the only thing I need to know to calculate the potential at point A is how far am I away from Q1 and what's its charge, and how far am I away from Q2 and what's its charge. Now, in this example, Q1 is negative 50 microcoulombs, Q2 is positive. So notice the net charge that I'm working with is 0. Now I'm closer, at least point A. Point A is closer to the positive charge, and it's farther away from the negative charge. Now they've given me the distances. This is actually 60 centimeters away, this is only 30 centimeters away. So what that tells me is that the electric potential at point A is going to be a positive value. Because, again, the charges are the same magnitude, opposite signs, but I'm farther away from the negative one. What's going to happen at point B? What will the electric potential be at point B? And at point B, I am evenly separated. I have the same distance from point B over to the positive charge and the negative charge, so the electric potentials will cancel out. And let's see what the formulas actually look like. I can do the whole problem just using the formula for the potential due to a point charge. So for point A, I do KQ1 over R1, KQ2 over R2, and then when I get to part B, I'm using the very same formula. Now, the Q1 and the Q2 have not changed, but the R1s and the R2s have. So at position A, R1 and R2 had values of 60 centimeters and 30 centimeters. And when I follow the prescription for the formula, I'm ending up with a positive 1498 kilovolts from the positive charge, but minus 749 kilovolts from the negative charge. And that balances, well, it turns out to be plus 749 kilovolts. When I'm looking at position B, R1 and R2 both have the same value, and so the contribution from the negative charge and the contribution from the positive charge exactly balance out. And the voltage is 0. Now, what does that mean to say that the voltage is 0? Does it mean that nothing is happening at that location? And one way to think about that is, if I were to place a charge at that location, how much energy would be required to bring the charge in from infinity or beyond to point B? And I could actually bring the charge in right here, and the potential would be 0 the whole way. And that would say that it wouldn't require any energy at all. I could bring a charge in from infinity to point B, and I would never have to exert any force in the y direction in order to bring it into point B. So if it's 0 volts, then it means that bringing the charge in from infinity to that location, the net amount of energy that I would need to use is 0. Okay, but it does not mean that there's no force acting on the charge. So there would be a force acting on the charge. It would be, if it's positive, it would be pushed away from the positive charge, but it would be drawn in by the negative charge. So just because the voltage is 0 does not mean that the electric field is 0, and vice versa. Okay, here's a problem that looks, to me it looks terrifying. Here is a charged ring. It's got charge uniformly distributed. What's the electric potential at that point? Now, we looked at this problem kind of similar to this when we were looking at electric fields. And with the electric fields, we had to keep track of components and such. Here we don't have to, because it's electric potential. All I need to know is how far away from this point is that charge, and then this charge, and then this charge. And you know, if this is a circular ring, and this is that perpendicular that goes right through the center of the circle, all parts of that charge are the very same distance from point P. And the distance would be x squared plus r squared, square root. And so I can take the entire charge and say it's all the very same distance of, I'm calling it little r here, is big R squared plus x squared to the 1/2. That's going to be the potential at location A. Now, what would happen if I took all the charge in that ring and I wrapped it around and concentrated it right at that point? How would that affect the electric potential? And it won't. As long as all the charge that we're looking at is at the same distance away from point A, it doesn't matter how it's distributed. Okay. So kind of an interesting feature, but also it leads to some possible trickiness, let me say, as far as figuring out these voltages. Remember, with the voltage, we just have to know how much charge there is, and for the charge, how far away is it. Take each sample of charge, divide through by the distance, multiply by k, and that will give you the contribution to the electric potential for that charge. Okay, back to uniform electric fields. Now, we kind of looked at this example before. We said that if we have a uniform electric field, that the voltage is going to drop off at a steady rate as we pass through this electric field. So we're going to introduce the idea of what are called equipotential surfaces. So there are surfaces, these green surfaces that have been defined, that are planes spaced between those two plates. This green line is going to be at some voltage, and this green line is all going to be at some voltage, and this green line. Now here, they've said that the surface of this plate is at 20 volts, and the surface of this plate is at 0 volts. They didn't divide this very evenly. I'm a little disappointed here. So this distance and this distance and this, those should all be evenly divided. We're certainly not, these are, well, I guess it depends on, it's a conductor, yeah. So these are definitely plates that are conductors. And so that charge is going to be right along the surface. That's where we've got to start measuring our voltages from. So yeah, they goofed up the picture a little bit. But what they're showing is that if it's 20 volts all the way across, then there's a steady drop. And so by evenly spacing those equipotentials, they'll all be separated by 5 volts for the example that they're showing us. Now, what happens if we have a point charge? Well, if I got a point charge, then the electric field is not constant, but I can still draw equipotentials. So surrounding a point charge, the equipotentials are going to be spherical surfaces, and what we can do is we can calculate these as kq over r. And so again, what we're finding is that the electric fields are directed away from the charges. The equipotential surfaces are surfaces that are surrounding the charge, and they're going to, well, in the case with spherical symmetry, surrounding a point charge, they're going to be spherical surfaces. And so these we can go in and we can just calculate what these values would be. So let's say that we've got, so in the example, I went ahead and used 4 nanocoulombs. Is that what they, I think that's something oh no, they did give that to us. All right, so this is the charge. I'm going to take K times that point charge amount, and then I'm looking to see what will be the R value for the 10 volt equipotential surface. I'm looking for that surface that is specifically at 10 volts. It says the 10 volt surface is located 3.6 meters away from the point charge. If I want to if I want to look at the 20 volt surface, I guess it's working the other way. So we're thinking of, here is the 10 volts, 20 volts, 30 volts. We're increasing in voltage, not in R. So as we're looking for surfaces that have higher and higher voltages to them, we're getting closer and closer to the point charge. And so we can map out where any of those equipotential surfaces would be. And if it's surrounding a point charge, they're all going to be spheres. And that would be the R value for each of the equipotential surfaces. And they pick some numbers that are fairly easy to calculate. Okay, so this is what equipotential surfaces are going to look like. Back in chapter 21 and 22, we said that we could draw these electric field lines. So let's draw the red lines in first. Those are the electric field lines, the E field lines. Once we've drawn those in, we can draw in the equipotentials by drawing surfaces where the surfaces are crossed by the electric field lines perpendicular at every location. I just have to make sure that everything is drawn perpendicular, and I'll have the equipotentials. Now, if these two charges are the same magnitude, and I can see that because I have the same number of electric field lines associated with the positive charge as with the negative charge. And they've spaced those pretty evenly. Those look just really well done. These charges are the same. So that says that there's going to be a plane right down the middle where the electric potential is going to be 0. At any location on that center equipotential, I am equidistant from the plus and the minus charge. And since one is plus Q and one is minus Q, the net potential there would be 0 across that center point. So here's an analogy that the textbook introduces, and it, here is a topographical map. And so these are representing elevations. Elevations are kind of like electric potential. So maybe I've got a, do we have a peak anywhere? So we might have a peak somewhere, and then that peak is surrounded by elevation surfaces, and that's kind of like these equipotential lines representing all the locations that are at the same voltage. All right, quick review here for gravity. Here's the big 4. gravitational force, gravitational field, gravitational potential, which we actually did not introduce, and gravitational potential energy. This is how they're all related. You are not expected to do all these derivatives and integrations, but this is kind of at the foundational level. We've got a couple of vectors. The force and the gravitational field are vectors. I have to keep track of direction. The energy and the potential are scalars. And so I don't have to keep track of direction. Oh wait, that was gravity. We're supposed to be studying the electric force. Oh my gosh, it looks exactly the same. Okay, so that means if you understand gravity, you understand the electric force. I know the electric force is a little more complicated because you got plus and minus charges. Ooh, wait, does that mean if you don't understand gravity, you don't understand the electric force? Anyway, here's the electric force, here's the big four. Again, it's force, field. The electric field is big E instead of little g. But the potential and the potential energy use the very same symbols. V and U, the same formulas up here, except that instead of the mass, we replace the mass with Q, with the charge. But everything else is analogous. You can kind of flip back and forth between those two and see that everything there is defined analogously. All right, we had looked at electric dipoles. We had introduced the idea of dipoles. We said dipoles are very important to us. We said that dipoles occur often in nature, in molecules, for example. A molecule that is electrically neutral overall can still have, and typically does still have, in most cases, regions of positive and negative charge on that molecule. And so we can model that as if it's equal amounts of positive and negative charge separated by some distance L. And so what we want to do is say, okay, if I have a dipole, maybe there's a water molecule here, what's the electric potential here? Now there's no net charge there. Does that mean that the electric potential is zero, or the electric field is zero? And what we found out is the answer to that is no. Because what happens is, if I'm at a point here, well, at this particular point, this point just happens to be closer to the positive charge compared with the negative charge, that means that point, the electric potential is going to be a little bit positive. If I were over here, well, then I would be closer to the negative charge than the positive charge, and that would say the potential on this half of the diagram is going to be negative, and the potential on this half is going to be positive. In fact, if we go back a few slides to here, that is a dipole, right? If you look at that, this is also a dipole, and that's what the equipotentials look like. All of these equipotential lines, this one was zero. This one's a little bit positive. This is more positive, more positive, more positive, most positive. As we get closer and closer, that gets higher and higher positive. And then this midline is all V equals zero. A little bit negative, a little bit negative, more negative, more negative, most negative, as we get closer and closer. So could we mathematically come up with a formula for this electric potential surrounding a dipole? And more importantly, do we want to get a formula for this? You go, I don't know. It's not such a bad example. Let's take a look and see. So here is the electric dipole. What I've done is I've used the same setup as I did for the electric field back in chapter 21 or 22. I guess it was 21. And so instead of putting L here, I broke it up into A and A. It makes it easier to write out the formulas. So the potential at point A is going to be KQ over R1, that's just a distance, and minus KQ over distance 2. Okay, and then there's an R. I'm going to say that there's an R that goes right from the center of the dipole out to point A, and then there's an angle. So the little r and the theta those are like polar coordinates around the dipole. And what we're going to find is that the dipole has cylindrical symmetry. If I think in terms of rotations around that axis, the equipotential surfaces, point A could be rotated around the x-axis, and all those points are going to have the same electric potential. Okay, so there's some symmetry we're working from here. Now, switching back and forth between x and y axes and these polar coordinates, that's going to be r cosine theta and r sine theta. Now, r1 and r2 are distances, and r1 is a little less than r, and r2 is a little bigger, and we can actually write those down right here. What we can do is say that distance 1 is equal to x minus a. So that's the effect of having the location here rather than at the origin. I can just subtract that amount from the x value. So notice point A is at the location of x and y. I'm using Pythagorean's theorem to say x minus a squared plus y squared, square root, that gives me r1. Similarly, r2 I can get by taking x plus a. So if I'm looking at the triangle, the right triangle that leads out to the negative charge, that has a length on this side of x plus an additional distance of a. So that's the difference between the r1 and the r2. Okay. Now what that leads to then is an exact formula for the potential due to a dipole. So if I'm at that location, the dipole at that location is going to be kq over r1 minus kq over r2. I just substitute in those values for r1 and r2, and that's what it looks like. Now it's definitely an exact formula. That's the good news. The downside of this is that it's hard to visualize what is going on, right? It's too complicated of a formula. So what we can do is this. We can try a simplification. We can say what would happen in the case where r is actually quite a bit bigger than a. That's often what we do with the dipole approximation, is we treat the distance between the positive and the negative charges as being kind of small compared with where we're making our observations. And so I wrote out, I expanded out this expression. That's going to be x squared plus a squared minus 2ax. It looks like that. And then the r1 value then can be recombined as x squared plus y squared minus 2ax plus a squared, all square rooted. And then what I did is I substituted in for x r times cosine theta. And then for x squared plus y squared, I substituted in r squared. So right at this step, I went from representing it in rectangular coordinates, and now I'm representing the distance in polar coordinates. So now I've been able to rewrite it in polar coordinates, and I'm hoping that's going to make more sense, right? Because polar coordinates, theta is being measured from the x-axis. So that's, I hope, is more intuitive. And then r is just going to say how far we are away from the origin. So I'm taking that exact formula and rewriting it in polar coordinates. And that would work. So I could just leave the r1 here. I've actually factored out an r at this point. And then I'm going to say 1 over r1 then is equal to 1 over r times this expression in terms of r's and thetas. And then I'm using an approximation. So at this point, I'm using what's kind of a standard approximation in physics, but you're not expected to be so familiar with these. And the approximation gives us a formula where 1 over r1 is approximately equal to 1 over r, 1 plus a over r times the cosine of theta. Now again, that's assuming that we're a fair distance away. When I substitute in these approximate formulas and carry out the algebra, I get to a formula that looks like this. It says that the potential at point A is given by kq over r. Now that's the old formula for a point charge, but it's going to get multiplied by 2 times A. Now that's the distance between the two charges in my dipole, times the cosine of theta divided by r. Now those can be brought together, and the electric potential then surrounding a dipole is K times the dipole divided by r squared. Now again, remember, because we're getting cancellation between the plus and minus charges, the potential here is going to drop off more rapidly. Now we don't get complete cancellation because the plus and the minus signs are not superimposed right on top of each other. There's a little bit of separation. And so the electric potential that we end up with is going to drop off like r squared. So it's dropping off more rapidly. And then what's also useful here is that the angular dependence is a cosine theta. Now that says that when theta is equal to 0 in the forward direction, that's where the electric dipole is the largest, or the electric potential is going to be the largest value. As theta swings around towards theta is equal to 90 degrees, or pi over 2, that's where the potential is 0. And then if I continue out to 180 degrees, cosine of 180 is -1. So that cosine theta factor is keeping track of how the potential goes from positive to 0 to negative, and then back to 0 and back to positive when we circularly walk around the dipole. So again, the potentials are scalars. We didn't have to do any x and y and z components, but there's still some challenging parts of the derivation that we've got here. Okay, just and I thought a useful example to see how some of these approximation formulas work. Okay, so let's get back to a relationship between electric potential energy and potential. Now they're going to introduce this unit of the EV. Again, historically it was called the electron volt, but I think now it's more common to just call these EV. And let's look at some formulas that we have for calculating electric potential energies. And so let's say that we have two charges, Q1 and Q2, and they're separated by a distance r. What we said earlier, in an earlier slide, we introduced this formula and said the potential energy associated with two charges separated by some distance r is given by little k, the electric force constant, times Q1 times Q2 divided by r. Not r squared. For potential energies, it's just one factor of r. And so for plus plus or minus minus, those would be repulsive forces, and the potential energy would be positive. For plus minus or minus plus, the potential energy will be, it's an attractive force, and the potential energies will always be negative. So I can just put the signs in, and the signs will take care, the signs on the Q's will take care of the signs on the potential energies. Okay, that's going to take care of itself. What happens now if instead of two charges, I have 3, or 4, or 5? What happens if I have a series of point charges? Well, what we can do is we can write out that the total potential energy here is related to the potential energy associated between Q1 and Q2, the potential energy between 2 and 3, and the potential energy between 3 and 1. What we can do is we can match up these charges in pairwise combinations, 2 at a time, and every 2 at a time that we can come up with is going to contribute to the overall potential energy. So it says that the potential energy here would be kq1, q2 over whatever that distance is. and then kq2, q3 over whatever that distance is between 2 and 3. So I do have to have, in order to carry out this calculation, I have to know what all the distances are. And I have to know what all the q's are. But I can systematically go through. Now you can see that this is kind of a symmetric formula where everybody is, all the charges are present in that formula in kind of the same manner. That's what we look for in physics often. Here in this slide, they're just introducing the unit of EV. And so they're coming back now and defining an EV as 1.6 10 to the minus 19 joules. And so we can switch back and forth. Whenever we need to be in standard units, we want to work in terms of joules. If we want to do a quick calculation of how much potential or kinetic energy is present, often using EV is faster. So here's an example. What if we have a set of plates, and this time, instead of electrons, we're going to be accelerating helium nuclei. Now, helium nuclei have a charge of 2 times the fundamental charge. That's 3.2, 10 to the minus 19. If the voltage between these two plates, I think this is the same voltage we used before, right, is 5,000 volts, then the potential energy that we're working with, that we're starting out with, would be Q times V. That would be 2 fundamental charges, because it's a helium nucleus, times 5,000. That would give us a potential energy of 10,000 eV. So that tells us by the time the helium nucleus exits the region between the plates, that all of that potential energy is now going to be converted into kinetic. And that gives us 10,000 eV of kinetic energy. Now that was easy to calculate because the charge of an electron, the charge of a proton, the charge of a helium nucleus, all of these things are going to have multiples of E, and that makes the calculations very quick. But if we want to calculate velocities, for example, we're going to need to convert the EV back into joules, and so that's what I've done here. I've taken that EV number of 10,000, multiplied by the conversion factor for joules. Now the conversion into joules is the very same conversion of how many coulombs are there in a fundamental charge. So there's not a new number to remember or memorize. It's a number we've worked from before. And this is how many joules of kinetic energy those helium nuclei will end up with. Now I've also got to take, in order to calculate the velocity, I need the kinetic energy, and I'm also going to need to know the mass. And these both need to be in standard units. I was able to get the kinetic energy converted into joules. What's the mass of a helium nucleus? And because there's 2 protons and 2 neutrons, and each proton and each neutron, to a good approximation, is 1 atomic mass unit, I just went with 4 atomic mass units. Now, a kilogram is the equivalent of a kilomole of atomic mass units. That's the way the connection works with atomic mass units. If I take 1 mole of atomic mass units, that gives me a gram. So to get a kilogram, I need 1,000 moles. And 1,000 moles would be a kilomole, and that would be 6.022 10 to the 26 atomic mass units. So that tells me the mass of my helium nucleus, to a good approximation, is going to be 6.64 10 to the minus 27 kilograms. And that number can go into my formula right here. Then I can carry out the calculation. The kilograms in the mass will cancel the kilograms in the joules. I'll take a square root. I'm going to be left with meters per second. So again, this is one of those standard units in, standard units out sorts of calculations. If I'm working with forces or kinetic energies, more likely than not, I really need to convert everything into standard units so that I can just get standard units coming back out. And the speed that we got for this helium nucleus is 6.94 10 to the 5th meters per second. So I think the example we did before was with an electron, and with the electron, the mass of the electron was much, 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 much lower, and so the electron came out much faster. But for the helium nucleus, we can still carry out these calculations using, where did this all start from? And it all started from voltage. It started from electric potential, using the electric potential to calculate kinetic energies. All right, let's use this same idea and think a little bit about the hydrogen atom. Now, in the hydrogen atom, I think we've talked about this before, the proton, to a very good approximation, the proton can be thought of as a point charge. That's not an issue. So the proton is taking up such a tiny amount of space that we can treat that as, and it's so much heavier than the electron that to a good approximation we can treat the proton as if it's just kind of sitting at rest. Doesn't take up that much space, and so that is really well represented as being a point charge. The electron is not. So the electron in an atom or a molecule, and this is kind of the simplest atom we could come up with, this electron is going to be spread all over. So the electron needs to be represented as a probability distribution of negative charge. It's not like right there is 1 unit of negative charge. It's like 1 unit of negative charge spread all over. And so what we could do is this. We could say that what's kind of an average, typical representation of how spread out the electron is. And what they're suggesting we use is this right here, 0.529 10 to the minus 10 meters, also known as 52.9 picometers. So atoms are really tiny. So they're saying, okay, this electron stuff, that's too difficult to deal with. What we could do instead is let's just pick kind of a representative distance of how far the electron probability is from the nucleus. And so they've given us a distance, and we can calculate a voltage. So if I place the proton right here, and I come out to a location 52 picometers, 52.9, from the proton, and plug those numbers in, I actually get 27 volts. So you're thinking, that's interesting. These atoms are tiny, 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 really, really tiny. The charges are relatively large. You know, the forces that we have within atoms are fairly large when we think about how tiny they really are. And so, 27 volts of electric potential within, due to the presence of a proton inside hydrogen. Now, how much potential energy then would that end up with if an electron were thought of as existing just at one location, 53 picometers from the proton, and that would be minus 27.2 eV. So that would be the potential energy of the interaction on average, the potential energy of the interaction between the proton and the electron within a hydrogen atom. There's that much. You could think of this as kind of a binding energy, but more specifically, let's think of it as an electric potential energy. Now, it turns out that's the actual number. When we use a bunch of quantum physics and we treat the electron as a probability distribution and we average over the entire probability distribution and carry out this calculation, that is the number we get for the potential energy. So they didn't pick this value just randomly. They picked a value that when we do much more detailed calculations, that is the number we get. So again, that's something to kind of think about and think, wow, 27 eV worth of potential energy. It's an electric potential of 27 volts. Now, that's not the whole story, so it's not really the binding energy, and that's why I kind of hesitated at saying that. So U by itself does not determine the binding energy because there's also a kinetic energy for that electron. The electron has a finite amount of kinetic energy, and so what we got to do is add together the kinetic energy and the potential energy together. Now, it turns out that going back to Physics 3A and the early part of this semester, we can bring in the electric force and we can do a very simple model, let's say. Let's say that we have a proton here and that the electron is in a circular orbit. Now, that's just not the way atoms and molecules work, okay? And unfortunately, a lot of times students are kind of stuck on this because it's conceptually, it's an easy model to think about. That's not what's going on. On the other hand, if we use the value of R that they gave us, and we carry through equations with circular motion and equations with a force holding the electron in a circular path, we can use that just to get a rough approximation as to how much energy we've got. And so I'm carrying through the formulas for, this is just acceleration depends on force divided by the mass of the electron. This is my circular motion kinematics equation, and we're just putting all this stuff together. And what it tells us is that if this were the case, the speed of the electron would be 2 million meters per second, okay, which it's not. But we can also use kinetic energy formulas, 1/2 mv squared, and it actually gives us a prediction. It says that the predicted value based on this model is that the electron would have a kinetic energy of 13.6 eV. When we do the full-blown quantum mechanical calculation, that's what we get. And so, again, these formulas can be used to come up with some reasonably good approximations. And in this case, we're going to say they're basically match the correct numbers. And so with an electron and a proton attracting each other here, we've got a potential energy of minus 27.2. We've got a kinetic energy of the electron of 13.6. And that says that the total energy of combining the interaction and the kinetic energy of the electron, and the kinetic energy of the proton is really small, so that's been ignored. But that would give us a binding energy of 13.6. Okay. Now, the reason we're going through all this is because this is chemical potential energy. So anytime I run any kind of a chemical reaction, if there's energy released, where is the energy coming from? And what we can do is for every chemical bond that we look at, we can think of the chemical bond in terms of electrons and nuclei attracting each other. So let's do this. Let's move on to the hydrogen molecule and say, here's an example of a chemical bond. Here are the two nuclei in the H2 molecule, and here's a couple of electrons. Now, a pair of electrons is equivalent to what we call one chemical bond. Now, the electrons are not located at distinct points. Again, they have to be treated as probability distributions. But let's just, again, use a very rough approximation and see what we come up with. The bond length in H2, in the H2 molecule, is 74 picometers. And that says that if we place the two nuclei at a distance of 74 picometers away from each other, and then I'm just going to put the electrons here, the same distance, and I'm going to make a square. So I'm going to put two electrons at two of the corners, and protons at the two of the quarters. And then I'm going to use our formula, KQ1, Q2 over R, and say, what are all the potential energies that we have to keep track of here? Well, if I look at this, what I've got is I've got 4 attractions going on. I've got this attraction between this electron and proton. I've got this between this electron and this proton, this electron and this proton. So I got 4 attractive forces, and I have 2 repulsive forces. The electrons are repelling each other, and the protons are repelling each other. And so in my potential energy formula, here are the 2 repulsions, and here are the 4 attractions. Now the R value for the repulsions is 74 picometers. Doing a little bit of geometry here, a little bit of Pythagorean's theorem, I've been able to calculate what the distance is between, on the sides. How long are the sides of the square? Those are 52 picometers. So I plugged those numbers in and carried out the calculations, and what I ended up with, and I used a shortcut along the way, you can show that Ke squared is 1.44 eV times nanometers. So I worked in some different units there. You could work in standard units also and get joules and convert to EV. But I ended up with the overall potential energy associated with these 4 charges interacting with each other at these distances would be minus 71.9 eV. Now I need that number to be negative in order for a molecule to form. In order for a chemical bond to be stable, I have to show that by forming the chemical bond, the attractive potential energies that go negative more than offset the repulsions. The attractions have to more than offset the repulsions. And now that we've got a few formulas to work from, that's a pretty powerful thing, right? So we've been able to go through and show that certainly we can arrange electrons and protons in a manner where they attract each other overall. Even though I got 2 repulsions, the 4 attractive forces are more than compensating. And so I've got a negative potential energy. Now what I haven't done here is I haven't gone in and estimated how much kinetic energy the electrons would have. So the electrons are going to have some amount of kinetic energies also. So that's not the final binding energy, but it's just kind of an idea of how we can look at a chemical bond and calculate or assign a certain amount of potential energy and kinetic energy to the atoms. All right, let's take a bigger molecule. One of my favorite molecules is glucose. Glucose. And so here's a glucose molecule. How many chemical bonds do we have there? A lot. And so here is the glucose molecule. And it's got a bunch of positive and negative regions to show that where all the OHs are. Anyway, what is chemical potential energy? Chemical potential energy is just electric potential energy. Because if we take the glucose molecule and react it with a bunch of oxygen, we get a bunch of carbon dioxide and a bunch of water. What I can do is think of this as, compound A reacts with a bunch of compound Bs, and we get a bunch of compound Cs and compound Ds. Now, energy is going to get conserved. And so that says that if I take the kinetic and the potential energies of all the chemical bonds, so each chemical bond is going to give us a potential energy, and the potential energy is going to be negative. The electrons are all going to have kinetic energies. We need to have the chemical potential energy, or the electric potential energy, be negative enough that this molecule stays together. And certainly glucose is a pretty stable molecule at 300 Kelvin at everyday temperatures. Here is the oxygen, same thing. I've got kinetic energies in the electrons and some kinetic energies in the nuclei. And then I've got potential energy due to the interactions of the electrons with the nuclei. And then I'm going to form CO2 and H2O. Now you may be familiar with the idea that when I react glucose, we say glucose contains a lot of chemical potential energy. We can release a lot of energy when we react it. And what that says is the potential energies of these chemical bonds in CO2 and H2O are deeper than they were in these molecules. These molecules are referred to as being more stable. More stable means that the electrons on average are able to get closer to the nuclei. So a more stable chemical bond just means that the electrons in the nuclei are able to get closer to each other, and the overall potential energy goes more negative. And so at the end of the day, in this reaction, the kinetic energies of all the products are much, much higher than the kinetic energies going in. And what that tells us is that the potential energies that we end up with are much deeper in these particular chemical bonds than they were here. And that's it. All of the chemical potential energy, chemical bonds are based on these potential energies. So, so this is a good place to wrap things up with chapter 23. I think I'm going to go back and just have that picture of glucose as the last slide. Again, if you guys have any questions, stop by office hours. Let's get whatever questions you've got looked at for this chapter.